All right, so now that the recording has started, I will just say that we're going to wait a couple more minutes for people to start trickling in or finish trickling in, and then we'll get started. All right, let's go ahead and get started then. So welcome to the UNC-Duke Joint Physics Colloquium. Today, we're going to listen to Sara Haravifard give our colloquium on experiments with quantum materials. Before getting started and before the introduction, I want to say a few words about the mechanics of this colloquium in this format. And it's very simple. Basically, if you have short questions, please use the raise hand option here on Zoom, or you can unmute yourself and ask a quick question, or in any way let us know. If there are longer questions, please wait until the end. There'll be a period for questions at the end, and otherwise, please, as most of you have already here, or all of you, stay in this muted microphone form. And I think with that, I'll turn to Josh Sokoler, who will do the introduction.
Thank you. It's my pleasure to introduce today Professor Sara Haravifard. Professor Haravifard did her PhD work at McMaster University in Hamilton in Canada. She worked with Bruce Gollin on neutron scattering studies of low-dimensional quantum magnets. She then spent 3 years as a postdoc and some time, or 2 years as a postdoc and some time as a research scientist at Argonne National Lab and the University of Chicago, where she began or continued to study two-dimensional quantum magnets, studying such phenomena as Bose-Einstein condensation in spin-half dimer systems. And she came to Duke in 2015, where she's now the William M. Fairbank Assistant Professor of Physics. And she also works quite a bit at Oak Ridge National Laboratory, where they do the neutron scattering experiments. There are things one doesn't learn doing a postdoc and research in the Midwest. One of those things is that you have to come to North Carolina to learn, or perhaps to the Duke Physics Building to learn, for example, is what to do if you come into your lab one morning and discover that the whole thing is covered in a layer of pine pollen. Professor Haravifard has dealt with such issues. And despite these challenges, she's kept her focus on fundamental physics, no doubt motivated by all the exciting theoretical and experimental phenomena that are being discovered right now in the realm of quantum materials. And I'm interested, as I hope you all are, in hearing what she has to tell us today about those. So, Sara, take it over.
So thank you very much for the invite, and thank you, Josh, for the nice introduction. I really appreciate this opportunity to talk about our research at Duke and through collaborations with national and international institutions. The title of my talk is Experiments with Quantum Materials, and I will give a little bit of a brief introduction on what I mean. But before doing that, because I'm going to show a lot of data as examples, I would like to acknowledge everyone who has been working with us and giving us insight, either through theoretical work and collaboration or the local contacts who have been helping us at the national facilities. So I would like, because the list would have been very long, I've decided to just acknowledge them through their institutions at this time. Okay, but this is not it, right? So my sincere gratitude is toward my team, who are excellent and wonderful scientists and researchers, from undergraduate students to graduate students to postdocs. None of the things that I'm going to show to you would have been possible or close to possible without the day and night dedication and ethics and the hard work of my team. So I really appreciate what they are doing, and I am forever thankful for them. Okay. So I would like to first start by giving you a little bit of an introduction of some of the top and hot topics in quantum materials and the ones that are close to my heart. So one of them is quantum spin liquids. You may have heard about them. I am not going to go into much details. I have added some references, so in case you're interested, please go ahead. And if after the talk you're even more interested, I can provide more references. So quantum materials, they have different categories, and these are the compounds that quantum mechanical interactions is going to be very important and is going to determine their properties. So a class of these exotic materials is called quantum spin liquids. However, these quantum spin liquids, they have very much distinct signatures. And this, I will explain to you, is one of the challenges to try to probe them experimentally as well. The very first one and the most important characteristic of a quantum spin liquid is the absence of ordinary magnetic order. So when absence of something is going to be the signature for it, you can just guess how difficult it can be, because it's not only that these compounds that they have the absence of magnetic order, there could be other compounds that also do not have magnetic order due to different reasons, but the absence of it is, at least if something does have the absence of magnetic order, can be a quantum spin liquid candidate. So then after that, there is going to be these fractionalized excitations or spin-ons that they can host, which I will explain a little bit later on. And in addition to that, there is going to be long-range quantum entanglement. So this is very key and very important, because it is going to practically put quantum spin liquids in the exotic category because of these long-range entanglement that they can host. So initially, in 1973, it was Anderson who proposed that this quantum spin liquid can actually be practically just a ground state of a system that has antiferromagnetic interaction between its nearest neighbors, and it does have a triangle lattice. So later on, folks became even more interested in this idea of quantum spin liquid. When Anderson came back with a more interesting idea, that okay, so I am talking about entanglement and fractionalized excitations, but also what I'm going to talk about is the fact that if we understand the physics behind the quantum spin liquids, maybe we can also understand the connection to the high temperature superconductivity. Practically, when we have these Cooper pairs, what is the glue that makes them work together? And in this entanglement that we have in the quantum spin liquid, what is this glue again that makes these spins entangled? In just very in general audience type of explanations, but that actually raised a lot of interest because now it is linking two of the giants in the field of quantum condensed matter, superconductivity and frustrated magnetism. So here you can see the two references that I just mentioned that you would be able to study more if you're interested. Now, in this talk, I am going to focus a little bit more on the frustrated magnets, and I will try to finish all the compounds, but at least I will definitely keep the focus on the two-dimensional frustrated systems, and hopefully, if there's time, we are also going to talk about the three-dimensional frustrated systems. So, in a two-dimensional frustrated system, the very first idea coming from Anderson was that what if you have a triangular lattice? And what should I add here is that it is going to have some sort of an Ising interaction. So we are kind of pinning these spins along a particular axis. So they're not like a Heisenberg that they can move around and be free, but they're going to be pointing along one particular direction. So now imagine J is going to be antiferromagnetic. So in this scenario, if you have one spin down, you can have another spin up and they will be happy. However, there is going to be too much talking with the third spin. So this guy is becoming frustrated because does not know which way to point. And actually, in that case, you're going to have a total of 6 different ground states that you can imagine. So if you're actually pointing it up, this guy is going to be happy, but this one will be unhappy. You can pointing it down and so on, and it can actually change between them. So this is a very basic idea of explaining what is going to be frustrated magnetism, and it actually gives birth to the idea of resonating valence bond as well. Now, in this case, your geometry is going to be the very key component. However, sometimes, in addition to the geometry, if there's going to be some sort of a competition between different interactions, we can also induce what is called frustration. So, for example, if you consider a square lattice, ideally somebody can come up with a sort of interactions. Again, these interactions are antiferromagnetic, that it would be some sort of a long-range nail-ordered state. However, if the J prime and J start to compete with each other, then you can get into the point that there is going to be a frustrated scenario. And again, the ground state is going to be a combination of different states. So in that case, I'm going to talk about what is called the Shapley-Sutherland model, and I will just explain a little bit of one corner of the phase diagram for these type of compounds. In 3 dimensions, recently there is one compound has been discovered, which is called the breeding paracore. So the breeding paracores, they're calling them breeding because it comes from the fact that it kind of shows inhale and exhale. So let's look at this. This figure that I'm showing on the left is showing just a paracore structure. So you have this corner touching tetrahedrons, and then again you're having this triangle, so you can geometry is going to introduce some frustration. R and R prime are going to be, for example, the size of these interactions, these tetrahedrons, and the J prime is going to be equal to J. So the nearest neighbors and the next nearest neighbors are going to have same sort of interaction. Now, imagine if you start to change the symmetry, lower it, in a case that, for example, the down tetrahedron is going to be much larger than the up ones. So in this scenario, so the first thing that happens is that the symmetry is now lowered, which again later on I will explain why it is important. And the R and R prime are no longer actually equal. So then you are now start to get into the situation that you can start to construct a phase diagram based on the ratio of the R and R prime, and also what would be the ratio between the interactions in the tetrahedron and inter and intra tetrahedron interactions, the J prime and J. Now, before I get to more details, I would like to explain to you a little bit about the resonance invariance bond, because this is the foundation of at least the very initial explanations of the quantum spin liquid case. So the valence bond, so let me start by talking about the valence bond solid first. So something that is very static, so there's no dynamic in it. So it is going to be this picture on the top left. So what is going to happen in that scenario is that there are going to be some bonds that are forming with a particular pattern to them. So it's sort of like it starts to show a crystallization of these bonds. And these bonds, when they are going to be formed, they are also going to start to introduce some local entanglement. So the pair of spins that are within each bond are entangled, but locally. Okay, so and they, of course, if you have now antiferromagnetic interaction between them, practically to have a non-magnetic ground state, it is going to form singlets. Okay, now there is going to be now a little bit more. Now, if we move a little bit more forward, and let's try to talk about the resonance valence bond, it is going to be a situation that you don't have necessarily a very configured pattern. So you can have a pattern, but still it is going to have some sort of a pattern. And in these cases, the ground state is going to be a little bit more exotic. Oops, sorry. Now, the key and what is going to be distinguishing the valence bond solid, for example, from a spin liquid, not even a quantum spin liquid, just a spin liquid, is even a classical one, is going to be that in the valence bond solids, these bonds order in certain patterns that break the lattice symmetry, while this is not the case for quantum spin liquid or a spin liquid itself. Now, this is important because if the symmetry is not broken, sometimes in the experiments, if there is going to be a candidate for this and shows, for example, non-magnetic state or a disordered state, then by looking into see that is the symmetry broken or not, we can distinguish is it really a viable quantum spin liquid candidate or not. Again, remember the absence of the magnetic ordering, even at the lowest temperature itself, is just a null result, right? So we can just look at it and say, okay, there's no magnetic peaks, there's no magnetic ordering, but there's still a lot of different things that we need to consider. Now, the ground state in the valence bond solid is not going to host a long-range entanglement, while in the quantum spin liquid, that is true that you can have a long entanglement, and these are the quantum mechanical fluctuations that are going to lead to that. And so these quantum fluctuations also are present when you're looking at the resonance valence bond. So these resonance valence bond is also very dynamic. So here, in the case of a long-range entanglement, you can see that not only there is no pattern, but also, for example, this spin here is entangled to the spin far away, or there's going to be, for example, this spin here that's entangled to this one. Now, one thing that I would like to note is that imagine that you are going to, for example, use neutrons to try to break these bonds. So what should we expect to see if we are truly going to have a quantum spin liquid? One thing that we can consider is that if you have a long range pairing of the spins and entanglement, so the energy that is needed to break them is going to be lower. So if you look, for example, at the excitations in the neutron scattering data, even at very low energies, you start to see some excitations that would tune with the energy of breaking these. And as we actually move up in energy, you can find other candidates that they have different energies. So a continuum in energy, for example, in the case of neutron scattering, is a key signature of having a quantum spin liquid candidate. Okay. Now, I am here also going to talk about these spin-ons, but again, this is going to be a rather very quick scenario of what these spin-ons are. So practically, spin-ons are going to be excitations or quasi-particles that can emerge when you have a quantum spin liquid candidate and you break one of these bonds. So if, for example, we are going to have here, for example, you're going to see that there is a spin a half, which is not in any bond, which is not entangled with anyone. So what can happen is that now this guy is a spin-on. So it does have a dispersion. It can start to move around. It is dynamic in a way that if you consider this bond here, what it can do is that it can break this bond and try to make another bond with this spin here and then free this spin here. So practically it can transform from this state to this state. So you can see that if we try to, for example, probe the spin-ons or these quasi-particles, which practically, I forgot to say this, sorry, spin-on is practically a spin a half without the charge, as you can see here. So when you break this and you try to reformat or reform the bond here, then you're going to have this bond, and then this spin is going to be left alone, and this is now the spin-on. So practically, if you map in the Q, you can see as a function of energy, there is going to be a dispersion related to the spin-ons. Okay. Now, let's get to actual real materials, because at the end of the day, as much as we appreciate all this theoretical work, but we won't be able to really understand the physics without having actual compounds in hand. So here I am going to talk about one particular compound, which actually turned out to be one of the most studied compounds in the history of quantum spin liquid candidates. So it is called ytterbium magnesium gallium oxide. So ytterbium 3+ with an effective spin of half, which is already good because it is close to quantum mechanical range and you can study quantum fluctuations very well in it. So this is going to be shown in the, is forming a triangle lattice. So practically you can see them here in blue. And then there is going to be non-magnetic isolating layer between them, which is the gallium and magnesium. One thing that you should note is that this gallium and magnesium, as you can see here, they do have a site mixing, which means that practically it is impossible for somebody who is trying to synthesize this compound to say exactly where the gallium and magnesium should be sitting in this layer. It would be random. So it can introduce some things into the play which are important, both positive and negative consequences. But let's just focus on the ytterbium ions, which are magnetic, and then let's see what is going on in here. So we are having a triangle lattice, as you can see in here, with the ytterbiums. So again, it goes back into this what we talked about in Anderson's proposal. Okay, so these are only the papers that have been published on this compound from 2015 to 2019. I stopped actually adding to this after 2019. But there are another 10 or so added to this. And what is interesting is that this debate and so much discussion about this compound, it's still going on. So it is very much a hot topic, and there's still a lot of discussion about it. And it motivated folks to actually start not only revisiting their theory, but also designing new compounds that, for example, the chemical disorder in them is less or it is more, to understand what that chemical disorder in the insulating layer is doing. So we were also interested to study this compound as well, and we started to look to try to grow large, high-quality single crystals of this compound. So the very first thing that I always explain to my team is that the quality of the sample is very important. So we have to always be sure that the samples that we are producing are very high quality, no impurities, as much as we can reduce the chemical disorder. So here you're looking at one of our main instruments that we use at Duke. You can see that it comes with two mirrors, elliptical mirrors, and it has two lamps that are on one focal point of these elliptical mirrors. It gets focused on the other point. So this point, which we call it zone, becomes actually very, very hot, up to 3000 Celsius. So we can actually grow all kinds of, I shouldn't say never all, but a wide range of materials that we can grow with the different melting temperatures. The way it works is that the compound that we want to grow them, we put them in a ceramic from top, and it's floating, so that's why it is called the floating zone image furnace. And then the seed rod, which could be a compound that we've grown before from the same family, or a very dense ceramic, is going to be sitting here. So this one from the top starts to move down. When it gets to the hot zone, it starts to melt, and from the viscosity, it actually gets into this other compound. So what is going to happen is that practically by moving, we can go through the zone, and we can come out of the zone, and we can make it very solidify, crystallization. So here, let's see if it works. Actually, my postdoc made this, so I was sure that's going to work. So here you can see the feed rod and the seed rod, and this is the zone that how they are going to actually be melted. And this is the crystal that's growing here, and this is the ceramic. So by rotating it, they are just going to make it more homogeneous. Okay. So there are advantages in this technique. For example, one way that somebody can say, okay, everything is floating, so therefore there is going to be no issues with contaminations. The temperature control is much wider, and the gradient can actually be controlled. So it actually helps us with making a wide range of samples. So in the case of ytterbium magnesium gallium oxide, as well, we use the technique. Here you're looking at the single crystal of this compound. So the whole thing is about 2 centimeters, is one single crystal. And here you're looking at the X-ray Lauer pattern of it. So it is, you can see that's a very nice hexagonal pattern to it. And all the peaks are very sharp. So it's a very high quality single crystal. This is the powder pattern for it. The data is shown in red, and in the black you're seeing the model. So it shows that there is no impurity, and the model fits very well with the data. So the very first thing that we should do in the case of where we have the compound and we would like to study them is the magnetic magnetometry or magnetic measurements. So magnetic susceptibility is the very first one. So practically just to see what happens if you apply very small amounts of field and try to change the temperature as the system goes through different magnetic states, what do we see? So what would you expect to see in the case of, for example, ferromagnetic ordering, antiferromagnetic ordering, and all of these things? Any sort of phase transition is going to, you have to start to see a sharp anomaly. So for ferromagnetic, it's different than antiferromagnetic. But in this case, you can see that we didn't see much happening. So it shows that down to the very lowest temperature, the system state disorder. Because if it would have gone into the ordered state, we would have seen a sharp anomaly in the data. And in these cases, actually, we use a specific setup, helium-3 setup. So we were able to go down to 250 millikelvin, 200 millikelvin. So the same, and the next measurement that can be done is magnetic measurements. So practically we look at the magnetic moment in the sample, the collective magnetic moment in the sample. Because we have a single crystal, we can apply field along different directions, and we can study the anisotropy of the compound. We can see that which way is going to require more energy for the system to break, to polarize its spin around, along that direction. So if it, for example, has a preferred orientation, a preferred axis, or a preferred plane, then in that case, depending on the direction of the field, it is going to require more or less energy. Here you can see that this is a field and this is magnetic moment. You can see that when H is parallel to the AD plane, there's going to be less energy required while magnetic moment is lower. And here you at H parallel to C, you can see it is going to go higher. So these are very initial measurements that can be done. But now here, when we try to now understand the data even better, we have actually went to National High Magnetic Field Laboratory in Florida, and we use a technique which is very sensitive. So this technique is called the tunnel dyed oscillator technique. So in a simple word, what I would want to say is that imagine this blue is our sample. So we put it in a coil, and then we look at the resonance frequency of the coil. So if the magnetization of the sample starts to change, then the L for this coil, this is an LC circuit. So the L for the coil also starts to change, so the frequency starts to change. So this is how the physics of it is working. But what is important about it is that it's actually very high resolution. So if there's going to be anything that cannot be seen with different methods, it can actually be seen in here. And the size of the sample that we can use can also be small. So here, for example, you can see frequency of the TDO, let's call this TDO, for H parallel to C at different temperatures, and for H perpendicular to C, again at different temperatures. So what you can see that is that for these two first, they show different behavior. So again, it's talking about anisotropy. It's talking about the fact that the spins, they have a preferred orientation, naturally intrinsic to them. And for example, we can start to move them or rotate them to go from H perpendicular to C to H parallel to C. You can see how it is changing. So this is one thing that we learned from it. But what the key is that, which we didn't see actually in our other measurements data, is that there is an anomaly that is happening. It's not as sharp as you would expect it to be for a long-range ordering, but there is something happening. So if you look at the field, say from 2 Tesla to about 4 Tesla, 5 Tesla, there is definitely something going on. The same is actually happened. And it is only at low temperatures, when we start to warm it up, it starts to wash away. So it shows that whatever it is, it has quantum mechanical nature to it. So these are actually the data, again, that is redrawn here. So you can see that it is difficult to see these sort of anomalies with the other techniques. We have to take the derivative of it. But when we take the derivative of it, then they do agree. Okay, so we decided to do some neutron experiments on this. And the key was that, okay, we already know that at from 2 Tesla or 0 Tesla to about 5 Tesla in our TDO data, something is happening. Let's go and figure out what is going on. So here what you're looking, these are the experimental data. The energy, So the energy is actually integrated all over. So it goes from almost 0 to about like 2-3 MeV. So all the low energy excitations that are talked about, they are captured in here and they're integrated over the area of interest. So at 0 field, you can see that there is excitations that are happening at high symmetry points, which it's called M. But when we start to go to 1 Tesla, it becomes more homogeneous. When we get to 2 Tesla now, these spectral weights are now moved instead of being at M point, now they have moved to this corner, which is a high symmetry point, K point. And then when we go to 3, 4, and 5, as expected, it starts to actually weaken. So this was one of the very important features that we discovered, and we decided to look into that more carefully. So these are the theoretical. So we have started to collaborate with theories. Of course, we wouldn't be able to do this all by ourselves, but they would then have different models, and they started to look at our data and tweak their model and their Hamiltonian to figure out which one is actually agreeing with this one. So here you can see different cuts, for example, and here again is showing that how these one peak that we had here now goes into 2 corners. So this is the theory and this is the experiment. So very well you can see that they are in agreement, and the features that have been actually included in the Hamiltonian does include those chemical disorder, some thermal disorder, and it also produces some scenarios of possible way that the spins are oriented. Now, this is the theoretical results, in a sense, I would say the results. So this was just short of full blast machine learning that was done on this compound. They practically are theory collaborators. They started to look at this and they started to make optimization of the parameters. So for example, they started to use the single Magnon dispersion, which is the simplest way that they would be able to just look at this, and it can actually happen when we start to look at the apply so much field that all the spins, they have nowhere to go but to align along the field. In that case, if we start to give them some energy, they will produce these quasi-electrons called magnons, and those magnons will have a dispersion, and then they can say, okay, so along this dispersion. That data was already published, but only for the phase that the magnetic field was very high, not these intermediate from 0 to 5 Tesla. So then they started to say, okay, let's look to see there is this change from M point to K point, and whatever model that we are going to discuss in here, this is practically all the parameters that are within this circle are going to be okay in the case of single Magnon dispersion. But also this change in the M and K needs to be addressed. So then they started to restrict the parameters even more, they started to restrict it even more, and then they picked the solution based on where this is going to be. This is a very important outcome of this experiment because there are many, many quantum spin liquid candidates out there that can produce hundreds of papers with high citations, but it turns out that most of them are saying that, oh, this is not a quantum spin liquid. Because as I said, it's very difficult to experimentally probe it. However, if we use a tuning parameter, for example, a magnetic field, and we can probe some other transition in the compound, then we would be able to restrict the parameters, and not that somebody that can come and pick a parameter here and some come pick a parameter in here, and then both of them are going to have the same answer. No, it is going to be very much strict. So this is the very important outcome of this paper. Not only just thinking about this one particular compound, but also thinking about the whole area of quantum spin liquids and how somebody needs to actually address that. This is an example of the papers that have been published and use different models. You're looking at the zero field here. This is our study, and these are the different parameters that have been used by others. And here, for example, you can see this is 1 Tesla, 2, 3, 4, and 5. As you can see, it's at M point, it becomes more homogeneous at 1, it goes to the K point, and then it starts to wash away. So this is very much in agreement with the experimental data that we saw. However, you can see none of the other ones can actually reproduce that. So it's very important. This paper was actually published in PRX. So this is very important just before making any sort of verdict about the quantum spin liquid to study that even in more details, to have a tuning parameter and try to model this, because the the parameter space is very wide. The Hamiltonian is very complicated, specifically if you have a compound which has a chemical disorder in it. So this is the summary for part 1, which again, I would like to stress on the fact that this is the importance of high quality samples, or even come up with samples that they have less chemical disorder in them, designing them, and the importance of high resolution inelastic neutron scattering are very important. And the key is to pick the right tuning parameter so that it can restrict the phase diagram. Okay. Now, I would like to now turn into the Shapley-Sutherland system because I'm not going to talk so much about the neutron experiments on this, but rather high magnetic field measurements. So the Shapley-Sutherland, or the square lattice that we just talked about, is going to be this sort of square lattice. Which was proposed by Shapley and Sutherland. You have these competing interactions, and in the case of competing interactions, both of them are antiferromagnetic. There are two cases. So one case is going to be J prime over J is going to be smaller than a value. The case of J prime over J is going to be more than a particular value. Sorry. So in that case, if you're in this range, then the ground state, which can actually be solved exactly, is a non-magnetic singlet ground state. And in this case, it is going to be an ordered nil antiferromagnetic state. Now, originally, folks thought that this transition from a singlet state to an ordered state is going to be direct, but then later on, it was discovered that there is a plaquette state, which is actually connecting these two together. This is of an exotic nature that it is still not very much known it's not clear, it's not confirmed, at least very much experimentally, what is the nature of this. But whatever it is going to have a plaquette nature to it. Now, again, as an experimentalist, we have always been interested into trying to look at the compounds that they have real world realization of the theories. And here you can look at the strontium copper borate. Again, copper carrying a spin 1/2 is responsible for magnetization in this compound. So this compound is topologically real world realization of the Shapley-Sutherland system. So this is the Shapley-Sutherland system. You can see that we have these orthogonal dimers, and if I rotate it again, you have these orthogonal dimers. So topologically, you can map it. And its ground state actually can be discussed, explained with the Heisenberg nearest neighbor and next nearest neighbor, both antiferromagnetic, plus some spin orbit coupling like the Diolechisky-Muyara interactions. But what is important about this is that the J prime over J for this real material is about 0.63. It's just below that case 1. So the ground state of this compound is in a singlet ground state. So there are different tuning parameters and can be used to push this right to the plaquette state and later on into the ordered state, because it is so close to that critical value. Now, one other thing that's important is application of magnetic field. So if we start to apply magnetic field, we have a singlet triplet excitation or a singlet triplet gap, right? So we know that we are in a singlet state. If we start to apply magnetic field, we will have this Zeeman term that's going to kick in, and you have these 3 branches of the triplet as set -1, +1, and 0, that they can start to separate, and there's going to be a critical field that we start to have these triplets triple into these ground states. So in this scenario, it is actually very much like a Bose-Einstein condensate physics. So your singlet is the vacuum, your triplets are bosons with hard core repulsion, and your magnetic field is a chemical potential. So let's see what can be done with this. Folks start started from years ago, and many more papers have been published since then to try to push this to very high magnetic fields and see what is this condensation of the triplets into the singlet ground state is going to look like. So initially, they started to see these sort of plateaus. As you can see that this is a magnetization, and this is field. It goes up to 50, for example, Tesla. Nowadays in Japan, actually, they were able to go to 120 Tesla, so it's really high. So anyway, so they were able to look at these plateaus, and then they would say, okay, so for example, here, this is 1/8 of the M over M saturation. So this is, let's call this the 1/8 plateau, and then so on so. Now, what is important is that initially it was thought that these triplets are going to have just one triplet that is condensing into a singlet. But later on, rather recently, Frederick Miller, who's very expert in these fields, actually he came and discussed the fact that no longer there's only a triplet that is condensing into a singlet. It is actually a bound state of triplets that are condensing into a singlet. And this actually opened the door to new scenarios for this compound. Field-induced topological states. So in this case, initially what was discussed was that, okay, first of all, this compound has a very strong Jalushinsky-Muriera interaction, which is a spin-orbit coupling type of interaction. So if you have something like that, so here, for example, this is an experimental data, neutron scattering, this is Q, this is energy. This is 3MeV, this is a triplet excitation, but you can see that it has a shape to it, and you can see the three triplets, even at zero field, without any Zeeman effect, separated. This separation and the shape that they have been given is due to this DM interaction, is due to this Jalushinsky-Muriera interaction. So which means that if you start to look at this scenario, you are going to have the DM interaction making these sort of what can I call it? Giving a dispersion into these triplets, SZ plus, -1 and 0. And then if you start to apply more fields, there's going to be a bit more separation due to the Zeeman effect. Eventually, there's going to be a critical field, which you're going to have a Dirac cone, but instead of having a Dirac cone for fermions, here you're dealing with triplons, you're dealing with bosons, or with their excitation quasi-particle is going to be magnons. So that is why it is called a Magnon topological compound, or topological magnons, because here you're going to, instead of having fermions, you're having bosons and magnons. So this is what originally was discussed in this paper, and this is a theory paper, and later on this was a very high resolution neutron experiment that was done. So it was not very successful in convincing everyone about this fact, but at least it opened the door that this type of experiments can actually be done with neutron scattering and can be probed. So they discussed this, and they said at around 1.4 Tesla, there's going to be a Dirac cone, or there's going to be a touching. So that paper is also here, that was published in Nature Physics. Now, what did we do? So we actually started to go to very high fields to see that, okay, if we go to very high fields, what happens? But not only in a pure compound, but we started to actually punch a hole in these copper dimers, practically breaking them. And that hole was nothing but magnesium, which is non-magnetic. So with the magnesium, which is non-magnetic, we started to dope this system. So strontium, copper, magnesium, boron oxide, and magnesium sitting for some copper. Now, initially, I was trying to get to like 25%, 30%, 50%, and this was really difficult to do. As a sample grower and somebody who has some experience with the synthesis, one of the most difficult projects that I had was trying to get this in. Then thankfully, Mila told me that, why are you trying to kill yourself over this? Why don't you just try to see that if a smaller concentration of the compound also is going to show something? Then we decided to go really low because it's definitely much easier to go lower concentrations. So we went 2%, 3%, and 5%. To our very surprise, what we started to see is that, okay, so this is the first thing, this is the same 1/8 that actually you saw before. This is dm over dh. So I'm taking a derivative for you to be able to see it better. So this is for the 2%. You can see that the 1/8 is there, so it is agreeing with what we saw before, but there is a wiggle happening in here. In a 3%, the wiggle is even more. At 5%, it's even more. So then we started to say, okay, let's focus on this. Let's see what's going on in here. Did we really have enough concentration that would be able to push this into the actual, some new state? And so this is here the df. So this is the TDO measurement again, but we took a derivative so that it would be easier to see. You can see in the pure case, there's nothing going on. 2%, there are these anomalies that they start to show up. So in this case, what happened was that we started to collaborate again with the theorists, and what they have done is that they said, okay, in this particular case, if you look at the green dots, these are the impurity sites. So we started to randomly put these impurity sites and breaking these dimers. Originally, they talked about the fact that there is going to be a bound state of excitations as a function of field that are condensing into the ground state. But here, not only we have these bound states, but because we are now making these dimers break, there are going to be special cases that we have only the triplet or SZ equals to 1 also present. So one of these wiggles is also going to be representing to that. And these guys themselves, so the impurities themselves also can actually bound together, which is now, this is very important because creating a bound state of particles, given the fact that the concentration was really low, this was actually quite surprising to us. But again, when they started to look at this and then they modeled it, they say, okay, so the energy is actually in accordance in what you guys are seeing for these wiggles. So through this, we were able to discover these new states in the impurity doped strontium copper borate. So if I would want to summarize this, so pressure, field, chemical doping, all of them actually can be used to provide unique insights, and they can actually be used to provide what is happening at the quantum phase transition. There is a significant impact of a chemical doping, at least in this compound at very small concentrations. Remember, this compound has a copper oxygen layers, it has a gap, so it is very closely related to cuprate, high temperature superconductors. So initially people, when they started to look at doping of this, they were trying to make it a superconductor. And then later on now we discovered that truly these doped particles are forming these bound states, which is very interesting. So this is something that needs to be studied even furthermore. Or, for example, the fact that up to now we were not able to see superconductivity in this compound could be because we need a local probe to, for example, look at these things. And the topological nature of the Shapley-Sutherland system is also a hot topic that needs to be discussed. So I don't know, how much time do I have?
You have 8 more minutes.
3 more minutes?
8, well, actually 7 more minutes.
Oh, 7, okay, 7 is actually good. So let's then quickly go to the 3D frustration. So in the 3D frustration, remember we talked about the Paracore, so the Paracore with the different sizes. So the key is that up to now, there was no single crystal of this compound or something that would represent the breeding Paracore. So the breeding Paracores are very interesting because there is a theoretical paper that came out a couple of years ago that talked about the fact that they may host the Veil Magnus excitations in them. And the reason is that, again, you have lower symmetry. So your spin orbit interactions or these Dzioluszynski-Moriera interactions are much stronger, and they can actually start to induce these Veil Magnons, and which are practically these massless particles of definite chirality. So, but without single crystal, it's very difficult to understand these, because dispersion is important, application of fields is important. So we grew the very first single crystal in our lab for this compound, barium, ytterbium, zinc oxide. So this is a breeding Paracore compound, but it's again ytterbium 3+, carrying spin 1/2, is responsible for magnetism in it. So here I'm showing you only the ytterbiums. You can see from the Lauer pattern, it shows a very nice, very clean pattern, so it's very high quality single crystal. Now, initially the work has been done on the powder for this compound, so it was published in 2016, and then we got interested in that. But the very first thing that we noticed is that, okay, so this is energy, and this is Q. This is inelastic neutron scattering data at T equals 200 millikelvin. You can see that there are these excitations, which are crystal field excitations. But also, what is interesting is that if you would expect this to have magnetic origin, and if there was only just a single ion, there are calculations what the dispersion needs to look like, or the form factor needs to look like. At lower Q, we should have more intensity. So, which means that in this case, something is going on, because at lower Q, we don't have more intensity. If you actually make a cut, you can see where the intensity peaks up. So then the theories start to model this, and what they said is that in this compound, you have a molecular magnet, or you have a single tetrahedron model. So you have these tetrahedrons that are forming these molecular magnets, and they are the definition of the ground state is based on that. So, but we were interested on this compound because there were this discussion of the Veil Magnus, right? So this is the phase diagram for this, based on this theory paper. So that's the same theory paper that I mentioned, which talks about that if your J prime over J, which was this size, the interaction between the up and down, and your D, which is the DM interaction, or this spin orbit coupling over J, is going to have some values, there are some predictions at the points in the phase diagram that you will start to see these Veil Magnus. And the most important thing is that if we start to look at the energy as a function of Q, there is going to be cases that you have these level crossings, linear level crossings, that are going to practically be the Veil nodes. And if somebody starts to look at these in the high symmetry points, you can see that in the discussion for the theory predictions, they said, okay, these Veil nodes are going to have 4 different sites, and plus minus K000, 0 minus plus K0, and so on. And the colors are going to be the chirality for it. So in that case, so it's quite interesting to be able to look at this. But the first thing is that, is there really going to be any sort of level crossings, or is there going to be any sort of linear level crossings? So this is the ESR data of the compound, the single crystal, as a function of magnetic field with the field along the 1-1-1 direction. This is the calculation result. So in both cases, it shows that if the field is going to be along the 1-1-1, there is it's not very easy to see it here, which is very low energy, but at around 3 or so, there is going to be some linear level crossing happening here, and there are some avoided level crossings also happening here. So which means that the energy of these hosts for topological features is going to be very low. It's very difficult to look at them. So one of the things that we used, for example, was that, okay, so if we use the TDO again, but we go to 24 millikelvin or very low temperatures, because these excitations are going to be very weak, then are we going to see anything? And in fact, we saw. So for both the AC susceptibility and the TGO data, we started to see these wiggle rooms that are happening in this. Again, we also looked at the heat capacity data. So for the heat capacity, it shows that there is something going on at low temperature. So look at the temperature here. This is 1 Kelvin. We went down to 50 millikelvin, and this is as a function of field. So even at 0, you can see that there is a broad. The fact that it is broad, it shows that it is not going to have a long-range order, right? There is something else happening. So we still do not understand exactly what is going on. But if there is going to be any quasi-particles, here it is showing itself. And more importantly, if we start to look at the thermal conductivity, so for example, this is the thermal conductivity as a function of temperature for barium, lutetium, zinc oxide. So lutetium is the isostructure of barium, terbium, zinc oxide. However, it is non-magnetic. So whatever it shows should be only due to phonons. And this is actually what we are seeing. We are seeing that, okay, if we fit it and you check for K T to the power of alpha, and if you check it, it is more or less what you would expect if somebody only had phonons in it when you start to warm it up, and then the phonons will start to show up. However, if you look at the barium, terbium, zinc oxide, you can see that at down to very low temperatures, it has a different behavior and starts to saturate, which shows that something in addition to phonons is actually contributing to this fact. So this is now something that we are going to add in to the fact that, let me actually skip this one, to the fact that these are the neutron scattering data, and with the neutron scattering data, if we look at the 0 Tesla, 1 Tesla, 3.5 and 4.8, for the 0 Tesla, there is an agreement that is happening for 1 Tesla between the theory and the neutron scattering data. So you're looking at all energy integrated down to lowest energy and Q. Okay, so and this is the theoretical work for it. So you can see that they are in good agreement. At 1, they are also in good agreement. 3.5 is where it starts to actually deviate from the theoretical work, and at 4.8 this is completely different. Which means that when we are at high energy or high fields, it looks like we can capture the physics with the single tetrahedron model. But when we go to low energies and low temperatures, that's when the single tetrahedron models fails, and practically what we have is now the tetrahedrons start talking to each other. So we have intertetrahedron interactions, which can introduce these quasi-particles that can host the Veil Magnus. And this is the summary. So the most important thing is to be able to grow the finger crystal. In elastic neutron experiments are going to be very important, and theoretical calculations is needed to be able to understand the topological nature of these compounds. And here I leave you with the conclusions that frustrated magnets are effective candidates in exploring emergent quantum phenomena and topological states of matter. Tuning parameters like pressure, magnetic field, chemical doping can be used to induce quantum phase transition and map the phase diagrams. Or in the case of spin liquids, it can be used to actually restrict the parameter space. And technical advancements, especially in the sample environments, play a very key role, because for all of these, if you wanted to go to very high magnetic fields and very low temperatures, all are very demanding on the technological advancements, and it's very important. It should be considered as one of the key aspects, not only just it is a sample environment. It is very important. Thank you.
Thank you, Sara. Thank you very much for this very interesting talk. We have time for a couple of questions at this point. You can use the raise hand feature, or you can go ahead and unmute yourselves. Maybe we'll try to do this in an organized fashion. So if you have a question, you can raise your hand using the raise hand feature on Zoom. Any questions from my material science colleagues, perhaps?
I have a question for Sara. This is Christoph.
Yes, go ahead.
You talked about machine learning that you were using to figure out these patterns that you saw. I didn't quite see how that would work. Or so how do you train the machine learning, or is it so more like looking at causal correlations, or is it more the processing of the sort of the structure of the images?
So practically, what it does is that it starts to check. So practically, there's a lot of parameters in the parameter space, as was shown. So it starts by the very first one, the loose conditions, and then it puts the loose conditions in addition to some other conditions. In this particular case that I'm talking about, it starts to put the other conditions in, and then it starts to check to see which one of these combination of the parameters, because it's the Hamiltonian with many parameters in it. It's J prime, nearest neighbor interaction, next nearest neighbor interaction, all of these. So which combination of these parameters is going to, for example, satisfy the fact that at 3 Tesla, there's going to be excitation at K point, something like that. So it should solve all of these, and then starts to, it's like fitting a multi-dimensional space. So it starts to look at every scenario and then checks and then solves it, and then says, am I getting the excitations at this point at this magnetic field or not? And then if not, then it starts to put it away, and then starts to move toward the direction that is going to give the answer for the ones that are not going to satisfy the loose conditions, but the more strict conditions. Did it answer your question?
Yeah, I think roughly. Yeah, I mean, we do machine learning for image processing, so it's different story. So I guess I was just curious.
So
I can learn from that.
I don't seem to have a raise hand option because I'm a co-host or something. But could I ask a question? So the susceptibility measurements and structural measurements are showing the possibility of some very interesting physics happening. Do these things show up also in transport measurements? Are there, can you measure spin conductivities or something like that that would show unusual behavior?
Yeah, definitely. But in most cases, our samples are insulators, so it's going to make it difficult. But if there's going to be, for example, intermetallic compounds, then transport measurements are also going to be, for example, there is one thing that folks are very interested in studying is as a function of temperature, there is going to be insulator and metal transition. So all of these things that are going to give more information, but not in our case, not at least in these compounds. So we are looking at some compounds, for example, that are going to, we are then going to apply transport measurements for them, but you need to have, if it's completely insulating, then you won't be able to do the actual measurement.
All right, I guess unless there are any other questions from the audience, I can ask a quick question. So I'm strictly speaking not a 100% condensed matter person, certainly not so much on the structure of material side. but I am a Monte Carlo person, very much so. And so I was wondering, on the theory side, if you know how much people are able to do for these types of systems with Monte Carlo. Monte Carlo, of course, has a lot of limitations, the sign problem and such.
Yeah, the data that I'm showing, so I believe that the theory part was actually done with classical Monte Carlo.
Classical Monte Carlo, I see.
Yeah. So that one, this one, a lot is being done with classical Monte Carlo, not only for this, but also for designing experiments and looking at from the neutron guide how neutrons are coming, and then practically some folks actually in ILL in France, they can do the experiment before doing the experiment with Monte Carlo.
I see. Okay. Great. I think we can then, unless there are other questions, we can wrap it up here. Let's see. Let's wait a few seconds, see if there's one last question. All right. Looks like we can go ahead and thank you then for this very nice talk.
Thank you very much. Bye bye.
Yeah.